Okay, can I introduce I don't know if we are all the speakers only or someone else.
I think it says 8 people. So whoever,
Okay.
it doesn't say who it is, but there you go.
Okay, welcome everybody to the special session on stability analysis of dynamical system and applications, part 1. So the first speaker of the session is Professor Peter Giesel from Sussex University, and he will talk about computation of contraction metrics for the stability of dynamical systems. So Peter, go ahead when you can.
Thank you very much, Leonardo, and thank you very much for you and Iman organizing this session. So I will talk about basically 2 parts, the computation and a bit of the analysis of contraction metrics. And the computational part is work together with Holger Wendland from Bayreuth. So yeah, the first part will be about the analytical and theoretical foundations of contraction metrics, what they are, what they do, why we need them, and also a little bit, how we can find them. But actually, we will find them mainly through computation, and that's the second part about the numerical methods that we're looking at, meshless collocation, how to compute them, and then a couple of examples. So let me start with a bit of theory. So what we're looking at is an autonomous ODE. So x dot is f of x. X is an n-dimensional space. F has a certain smoothness, at least C1. We will need a bit more smoothness later. And the solution x of t of this ODE I will denote by st xi. So xi is the initial condition and t is the time. And what we are interested in is we want to find an equilibrium point that's stable, asymptotically stable, and then we're interested in the basin of attraction, which is the set of all initial values that will converge to this equilibrium point. And there are obviously lots of methods to determine such a basin of attraction. Set-oriented methods, so that would kind of separate your phase space into different cells and you look at the dynamics between these cells. You could try to find the boundary of the basin of attraction, which would be in invariant manifold. A very old and popular method is the method of Lyapunov functions, which in some way measure the distance to this equilibrium point. This distance must decrease. And today I want to talk about contraction metrics, and that is measuring the distance between 2 adjacent solutions, and this distance should decrease. So the idea is if the distance between 2 solutions will get smaller and smaller, they have the same long-term dynamics, and under some additional assumptions, these long-term dynamics will be an equilibrium point. And that idea goes back, well, to at least the 1950s here, has a long history. And some advantages of this contraction metric are it will be a local differential criterion that we can check basically at every point in our phase space or in the subset. We don't actually need any information about the location of the equilibrium, which is our attractor here. So we can generalize all this from equilibria to periodic orbits and in some ways even to more general attractors. But today I'm just focusing on the attractor being an equilibrium point. So we don't need any information about it in contrast to, for example, the Lyapunov functions where we would need to know where the equilibrium is. It will show existence and uniqueness of this equilibrium, give us information about the basin of attraction, so we will find a subset of that. And because it's not, the equilibrium point is not a special point, so it's actually robust under perturbations of the system. So if instead of the system you consider a different system where you slightly move your equilibrium point, you can still use the same contraction metric. So that was kind of a verbal overview. Let's go into a bit more mathematical notation now. So a contraction metric is actually a Riemannian metric, so something to measure the distance. And in our context, it's just a matrix-valued function defined on all x in the phase space, and with the values are symmetric n times n matrices. And additionally, they need to be positive definite matrices. So M of x is a positive definite symmetric matrix for each point x. And that defines a point-dependent scalar product. So VW would be defined by V transposed matrix M of x times W. If M is the identity matrix, that gives us the usual Euclidean metric. But basically, the idea is we have more freedom to choose the appropriate metric on each point of our phase space. And then the other notation we need is that of an orbital derivative, and that's the derivative along solutions of our differential equations. So V is a function, and if you plug in a solution x of t and take the time derivative of this, then that's the derivative of V along solutions. And you don't actually need the solution. You can calculate this by the chain rule to be this expression here. And similarly, we can do this for this matrix valued function M just component-wise. Right, so now we have all the tools. And before I give you the theorem, I want to tell you, give you the idea behind the next theorem, what the quantity is that tells us if these solutions contract. So what we want is we consider two solutions, one starting at x, and that evolves with time as stx, and then one starting nearby at y and evolving in this way sty. So that's the red one. And what we want to look at is the distance between these, and more precisely, we want to see the time evolution of this distance, because in the end, we want to show that this distance decreases as time increases. So we look at the time-dependent distance, actually the square of it, d squared t, and we measure this with respect to this metric m. So we take this distance vector, sty minus stx, or at this point here, transposed m stx, and then sty minus stx. So that's the expression of the distance we're considering. You could also look at the geodesic between these and the integral. Basically, if they are nearby, you always get the same criterion. I wanted to make it as simple as possible. And now what we want to do is we take the time derivative of this expression, and we call this distance vector between these here v. So taking the time derivative, I mean, we have three terms. So we first of all get the time derivative of this one here. And because they are solutions of the differential equation, they are f of sty and f of stx. This is the time derivative of m along solution. So it's just this orbital derivative. And then we have the same for the first term. And now we're using that they're kind of close by. So we use Taylor approximation for this term. So in first order, this here would be df times v, this distance vector. And the same for this term. So in the end, we get this expression here using that we're adjacent. We can make all this obviously precise. So you can see this is a very nice expression, and we want the derivative to decrease. So we want this to be negative, and even better, we would want it to be negative times the d square itself. So our assumption will be that this term here is bounded by a negative constant times v transposed mv. And this function here I just call Lm, and you can think of it as the contraction at the point stx in direction v. So if you're at this point, then solutions in this direction will be contracted. And then you can see, I mean, here you can immediately show exponential attraction. So this gives rise to this theorem. This Lm should be bounded by minus nu, and again the Lm is defined in here. So this again is the point x direction v. You have contraction, and you want contraction in all directions v. So we take the maximum of this with respect to all directions v which are normed, and you get this function Lm. And if this is bounded, and then you get exponential attraction with rate minus nu. The other additional ingredient you need that this holds in a set K, and we assume that K is positively invariant, compact, and connected. If this holds in for all points in K, then there is one and only one equilibrium, in K, which is exponentially stable, minus nu is the upper bound on the rate of attraction, and the sit K lies in the basin of attraction. Now you wonder, is there a converse theorem? So basically, if we have a stable, asymptotically or exponentially stable equilibrium, can we always find such a metric M? And the answer is yes. And this is one result which will help us to actually construct it later. So the result is, let me just go back again. What we essentially want is that this expression here of M is a negative definite matrix. And the result is basically you can choose this to be any negative definite matrix you want. We will always have a solution. So if you, that's this red equation here. So this expression on M, you can set to be a given negative definite matrix. So C is positive definite minus C is negative definite. And this is always a solution, a unique solution, which is a Riemannian matrix. So in particular, M itself is positive definite. So you can construct such a metric by solving this equation. Now, this is a matrix valued PDE, so it's not the easiest to solve, but that's what we will do in the next step numerically. Just a word to the proof, so you can actually write down an analytical formula that would need the solution, but it's not really helpful to really construct it. So let me rather go on to the second part, and I see I need to hurry up a little bit. So let me talk about the numerical method that we developed to solve this PDE. So let's recall we want to show existence and uniqueness of an equilibrium and determine its basin of attraction. And the tool is we want to find a Riemannian metric, and I call this S now because it's approximating the solution M of our previous equation. So what we want from S is S needs to be positive definite, and f of S, which is this expression here, this linear operator, needs to be negative definite. And again, there are a couple of other previous construction methods. I want to focus today on one using meshless collocation. So the idea is we want to approximate the solution of f of M is minus C. So here we can choose any negative definite matrix. We just choose a constant one for simplicity. And so what we're using here is we want to solve this linear operator f, this linear differential operator applied to M is a given right-hand side. We do this by collocation. So we give ourselves a fixed number of collocation points, and we want to solve this PDE. The solution will be the norm minimal interpolant at the collocation points. So at the collocation points, this will be solved exactly, and S will be the norm minimal function that does this in the appropriate function space. The function space will be a Sobolev space H sigma with values in the symmetric matrices, and there are error estimates available in terms of f of M to f of S. So M is the solution and S will be our approximation, our norm minimal interpolant. And the difference here can be made small by making hxk small. So that's the fill distance of our collocation points. So essentially speaking, the denser the points of x in k are, the better, the smaller is the error. And you have a rate of convergence that depends on the smoothness of your Sobolev space and the dimension. So that means if this error is small enough, because M is negative definite, S will be, f of M is negative definite, f of S will also be negative definite. And we have a similar estimate for M to S. And we know M is positive definite, so S will also be positive definite if we are close enough. So let me finish with two examples. The first one is a very simple linear example where we can actually compute the solution of f of M. We set the right-hand side to be the minus identity. And you can see, which is always true for linear systems, that the solution is a constant function. And so this is our numerical method. These are the collocation points. In the color you see the points, the areas where f, or in this case actually f of s, is not, doesn't have the right sign. So it fails to be a contraction metric here in between these points and up there, but otherwise it's a valid contraction metric with the right signs. And here is a visualization of the metric S by plotting curves of equal distance with respect to this metric. And what you can clearly see that it really isn't point dependent. It's a constant metric. So it's very closely approximate this one. And a nonlinear example is the van der Pol equation here with reverse time. So the equilibrium at 0, 0 is asymptotically stable. And again, here you see our collocation points. In red, the area where f of s is negative definite, or the boundary of that one, which is in here, and also blue is the boundary where s fails to be positive definite. So in here, it's a valid contraction metric. And here you can clearly see that the metric is not, it depends on the points, it really varies. And you get an impression of where you have more sensitivity in certain directions. So time is up. I need to stop here, but Iman, and I point to him later, will go on to develop these methods further. I come to that in the extensions. But I've shown you what a contraction metric is. It's a local property measuring the distance between adjacent trajectories. So with respect to this metric, this distance will decrease. It serves to determine an equilibrium point, and it's based on attraction. You don't need any information about the equilibrium. And the other advantage is it's robust with respect to perturbations, which we will see later. I've shown you a converse theorem, which characterizes this a contraction metric by a linear matrix valued PDE. And I introduced a numerical construction method by solving this with meshless collocation. Now, I've basically plotted a little bit where it fails to be a contraction metric, and that was basically just evaluating it at lots of points, which is not a rigorous way of doing it. But Iman later will tell you about a verification method that actually rigorously checks where the CPA, where this is a contraction metric and where not. So stay for Iman's talk. And we've also developed a similar metric method for periodic orbits, using also metrics valid PDE, which is contained in these two papers. And the first ones are about this talk. So thank you very much for your attention.
Thank you, Peter, for the nice talk. I don't know if someone has any question. We have 3 minutes. Someone in the chat. I have a little one question. Yep. Maybe it's too basic, but the system that you are working are not constrained, so you don't have constraints into your dynamical equation. For instance, non-holonomic constraints that have restrictions on velocities. When people work with mechanical systems based on Riemannian geometry, for non-holonomic systems, they use, instead of a Riemannian metric, a sub-Riemannian metric that encode also the distribution that define the constraints. Do you know if your approach and this research line that you were explaining here for the next steps can be also extended to the direction of system with constraints, for instance? Like restrictions in velocity, but changing the metric appropriately?
I must admit, I don't know very much about sub-Riemannian metrics, but it's definitely an interesting thing to look at. Because I don't know so much, I can't really affirmatively answer your question with yes or no, but it could well be possible to generalize that as well, to put more constraints on the Riemannian metric. But yeah, I would be very interested in learning more about it and seeing whether we can adapt that method to that problem.
Thank you very much. There is a question from David. He says, I assume that it is possible to work with second order differential equation typical in mechanics and nonlinear spaces like manifolds?
Yes. So I mean, the setup here is basically a first order system. So you would the way to do it would be to convert that into a second order equation. You can convert into a first order system of equations, and that would directly work. And we basically took the simplest case of Rn, but in principle you can look at Riemannian manifolds as well and kind of study them as well. Yeah, so yes to both.
Thank you. No more questions. Let's thanks the speaker, and Carlos is the next one. Maybe Ayman can introduce him now.
Yeah. Okay, we have the second speaker, Carlos Argaiz, who is a research specialist and a postdoc in the University of Iceland. He will talk about his developed software and code for computing Lyapunov functions.
Well, thank you very much, Iman. It's a pleasure to be here. I wonder, can you see my screen? Excellent. So, well, as Iman says, I'm going to talk about the US software we develop at the university, which is a natural consequence of the work we have been doing there. And this software is called LabShoal, and it's a joint work with Peter Giesel and Sigurdur Frey Hamstein. And let's just start from the beginning. So let us assume that we have an ordinary differential equation that is autonomous, something like the equation there. And then we know that a complete Lyapunov function is a scalar value function v from Rn to R that characterizes the qualitative behavior of the dynamical system, and that is defined in the whole phase space. Now, it has three main properties. So it's not increasing along solutions of the ODE. You can divide the phase space between a strictly decreasing region, which is the gradient-like flow, and a constant one, which is a constant flow that we're gonna call the chain recurrence set. So that would include the critical points, the orbits, and all these kind of things. And it must be constant on each component of the connected component of the chain recurrence set. Now, let us see an example. So I unfortunately missed Peter's talk because I had troubles with connection. So I don't know what you have seen in the past 20 minutes. So I hope I'm not redundant here. But let us assume we have a function like this. So this is an ordinary differential equation, it's autonomous, and by simple inspection, you can expect a critical point at the origin, and you can also expect an orbit at radius a half, or circumference of radius a half, and circumference of radius 1. So if we construct the Lyapunov function that characterizes that system and describes the behavior, then we hopefully expect to see something like that. And in fact, we do. This is the orbit of radius a half, and then the orbit radius 1, and then the critical point. So that's the basic idea of what we want to get. Now, how do we get it? So what we want to get is to construct the complete Lyapunov function. And the algorithm, sketching in it's something very simple. So we're gonna assume that the derivative of time of the complete Lyapunov function, which you can use the chain rule to get this differential equation here, that has to be lower or equal to 0. So we're going to assume that it's -1, and we already by hand know that it may not work perfectly well in the chain recurrence set when it has to be 0. So this is something that we're gonna use in our benefit, because then once we have solved this equation, then we can search for those points in which the equality fails to be -1, and that will isolate the chain recurrence set. So it actually is something good for us. Now, to solve this differential equation, we're going to use mesh-free collocation with radial basis functions to approximately solve the PDE. And to use mesh-free collocation, then we're going to set a finite set of collocation points, usually in a hexagonal shape, to when we are going to construct the collocation method to solve this differential equation. And sometimes this is something we optionally do we substitute the original system of x by another system that has the same solution trajectories, but that has the property of having norm 1 or almost 1. So that's what we call the quasi-normalization. And so this is the idea. So we're going to solve the PDE, and we're going to do mesh-free collocation on a finite set of collocation points using quasi-normalization. Now, since I'm going to talk to you about the code, I already introduced the formula. So we use radial basis functions, and we use wetland functions as radial basis functions. So an example of a radial basis function would be something like this. So this is a function that it's compact supported, it's a polynomial, and that has defined some auxiliary functions defined iteratively by this. Now, the explicit solutions, the explicit formulas to compute the complete Lyapunov function and the orbital derivative are these ones, in which you can see there is an xj, which is a collocation point, and an x, which has no j, that's the evaluation grid. So it means that to construct a complete Lyapunov function, we need two grids. One is the evaluation grid x, and the other one, xj, is the collocation, as I said, usually hexagonal. Now, beta, it's the solution of the collocation method. So that means we take the collocation method, we construct the collocation matrix, and then we give the condition that, as I said, is going to be -1. So beta is the solution of that matrix equation. Now, we have learned that once we have constructed a first complete Lyapunov function, we can just ask ourselves, how is the orbital derivative around each collocation point? And then we can take the direction of the flow and say, well, in these points around the collocation point, the orbital derivative behaves like this. So if I take the average, so that allows me to iterate on top of a previous constructed complete Lyapunov function. So for later iteration, we use that. And the matrix is constructed with this formula. So this is basically what we had to get written in our code. Now, what is the interest of our code? Well, the interest is to have a capability to analyze the stability of the chain recurrence sets, to describe both the gradient-like flow and the chain recurrence set. Now, we know that our approximation will fail in the area surrounding the chain recurrence set because V prime has to be 0, so it cannot be -1. However, our code also computes the norm, the gradient of the complete Lyapunov function. And we know that when the gradient is 0, then that's also the chain recurrence set. So we have two different ways to obtain the chain recurrence set. Now, we want to construct a complete Lyapunov function with the right orbital derivative. So that's why I talked to you about the iterations. So we can reiterate over the values of the orbital derivative, and that enhances the approximation. And we want to compute the eigenvalues and the eigenvectors. That gives a lot of information, for example, to classify orbits and or critical points. And to do that, we need to compute the Hessian. So our code computes the eigenvalues, the eigenvectors, and the Hessian. And our code can run systems from 1 dimension up to n dimensions. Of course, one needs to be careful with this because it is true we can run many dimensions, but then after several, it's difficult to analyze it. But in principle, we can do it. And of course, we want a code that is easy to play with. Nobody wants a code that is complicated, especially not us. We want something easy. So this is easy to play with. So basically, it's user-friendly. So that's what we wanted. Now, our code is in these settings. We have two versions, version 1, version 2. They're both written in C++. And all the algebra operations, the matrices and vectors manipulation is handled by the library Armadillo, which is very well parallelized, and for our taste is actually very fast. And to multi-thread several operations in the calculations of the complete Lyapunov function, we use OpenMP, which is a natural multi-threading for most C++ distributions. And well, this program was developed using Unix-based operating systems. So it runs very naturally in the command line. And we have also taken the time to verify that it runs on Windows. But in my particular case, I think from Linux is just excellent using the command. It's very simple, it's very straightforward, and it runs very nice. Now it has, of course, several outputs. It produces the outputs of the complete Lyapunov function, of the norm, of the orbital derivative, of the chain recurrence set, different outputs. But there are two main outputs that I want to talk about. The data LPX, which it's important to keep it because that tells us which parameters we use in the computation. For example, what's the density of the collocation grid, or what's the density of the evaluation grid, which parameters we use for the wetland function, etc., etc. All that is stored in data LPX. And then the output LPX, that's where all the natural printings of the running comes out. For example, when did the program start? When did the program finish? How long did it take, etc., etc. It's written there. Now, it is coupled with our previous software, Wetland Shoal, which we use to construct wetland functions. And since we were working in Lyapunov functions, so it was natural to construct all this in a coupled way. So that allows us to change and vary the wetland function we want to use. So we can use different radial basis functions of different order. We can do it with that. And version 2 is object-oriented programming. So it means that it's divided in classes. That allows us to reuse pieces of the code for different things. And that goes against the version 1, which was rather a functional programming. Yeah. Now, as I said, there are two grids we need to construct. So I'm giving you some visual input here, maybe to clarify that. So we have all these red little points. Those are the collocation points. And then all these blue points that are the evaluation points. So in the version 1 of our code, we had different options to evaluate the function. So we use circular and we use directional. Now, in the second version, we stopped using the circular and we use only the directional and some denser grid that it's all over the place. And the reason we do that is that because we have noticed that if we want to use iterations, our iterations are much better if we just take the information aligned to the flux, to the corresponding collocation points. So for that reason, we deprecated the circular grid and we just keep this one for the iterations. And then the program gives you also the option to say, hey, you can compute the iterations, but on top of that, you can have the evaluations with a denser grid, which is what we do in our work. We iterate with the directional grid, but all our results are analyzed in the dense grid. Now, the code is divided very simply. So basically, one could say that every different file is a different class. So you have instructions header, that's where all the input from the user comes. And then the problem CPP, that's what the main function is. And then the RBF, so that means the matrix, the collocation, the grids, that comes in the RBF class, which would be the CPP and the corresponding header. Now, generalities, that's rather for printing or timing or stuff like that. Now, the Lyapunov class, that's where the Lyapunov function is built, the orbital derivative is built, where the norm is built, where the Hessians are built, where the eigenvalues, eigenvectors are constructed, etc., etc. Now, the user has to modify the ODE system as much as the instructions. So that's where the user decides what system to run. And then the ODE tools, that's basically just the Jacobian or things related to the dynamical system. And then wetland.cpp, that's basically wetland shoal. So that's the code to compute wetland functions of any order for any smooth parameter. And just to finish, I just want to show you how the input looks. So you see, this is what the user has modified. So the user has different options here to run. So he can run only with the directional, which is much faster, but we usually recommend to run directional and Cartesian and analyze the Cartesian. That's, you know, iterate over the directional, but then analyze the values in the denser grid. Then you can also have the chain recurrence set and the eigenvalues only on the chain recurrence set, but that's also very useful to classify the orbits. And then you can compute the chain recurrence set using the norm. Now, more options are coming because we are constantly upgrading our codes, and very soon there's going to be a new version. Now, all the names, all the functions are very intuitive. For example, the user has to choose the calculation or define the ODE dimension. That's very intuitive, so the user don't get lost. So there is a section for the grid, there is a section for the eigenvalues, etc., etc. There is a section for the wetland function and a section for the multi-threading. And then finally, you can see some of our results. So this is a complete Lyapunov function for the original system I showed you at the beginning, but this one using quasi-normalization. This is the orbital derivative, then the chain recurrence set, and the norm of the gradient. And finally, this is how on the chain recurrence set, which are the two orbits and the critical point, how the classification of the eigenvalues and eigenvectors look like. So for example, for a critical point that it's a minimum, the Hessian would have two positive eigenvalues. And that's basically what I wanted to talk to you. And thank you, Iman, for the invitation. It's been a pleasure.
Thank you very much for the nice talk, Carlos. If there is some question, we have 4 more minutes.
Oh, I just want to tell something. I'm sorry, because this is important. Version 1 was developed with Hjörtur Björnsson from the University of Iceland and Jean-Claude Bertret from Robustness. And hopefully we will all continue developing more and more versions. There is at least one coming. That was it. Thank you.
Thank you.
I have
Other
a
question?
question. Yeah. Why? This is because I'm not a programming guy. But why you expose the code in C++? What's the reason of using?
Yeah. Well, I mean, my bosses uses C++, so that was actually a blessing because I think it's probably the best programming language you have. It's very fast. It's very well maintained. There is sufficient information on the internet, so you can, I mean, you have all the tools to become independent very quickly. And when you compare, for example, to Python or to MATLAB, for example, they're very useful also. I like them too, but they are not as fast. And I think C++ on that it's much better.
Okay, thank you. Thank you very much.
Thank you. Well, I guess there are no more questions. So
Yeah, thank you again, Carlos.
thank you, Iman.
And I start sharing my screen for the next talk.
Do we continue or we wait 1 minute more until the time?
Wow. There's some problem, I guess. Can you see the screen now?
Yeah.
Ah, but I see black myself. That's strange. Oh.
Okay, well, the next speaker is Ayman Mehrabinehad from Haskoli Iceland University of Iceland, sorry. and he will talk about CPA RBF contraction metrics.
Thank you. And thank you everyone for being here today. I will talk about how we, our method to how compute the contraction metric. It is a joint work with Professors Hofstein and Diesel. And fortunately, Peter gives a lot of good points about the preliminaries. It's mostly the same, so I skipped them. We consider an ordinary differential equation of this form, and we search for the exponentially stable equilibrium points and ask for the basin of attraction. The method we use is using Riemannian contraction metrics, which are local elliptic continuous matrix valued functions, which are positive definite at each point, and also having the property that this LM operator has the following property, or equivalently being a negative definite. So there are two things to check: M being positive definite and Fm being negative definite at each point inside the basin of attraction. Now, we know that if a contraction metric exists on a compact and connected positively invariant set, then we would have a unique equilibrium point there, and basin of attraction includes the set which has the properties of the contraction metric on. Inversely, if we start from an equilibrium point and its basin of attraction, then we know the solution of this matrix valued PDE would be the candidate for a contraction metric. Now, instead of solving it analytically, we use RBF functions to approximate it numerically, and putting all the settings accordingly, it would be the optimal recovery problem as to find a norm minimum solution for the approximation of that PDE. We are sure that it exists and it is unique, considering the situations are satisfied. Now, our algorithm has two main steps. The first one is solving this PDE numerically by using a set of collocation points, and then computing the norm minimal interpolation using radial basis functions. We use Wendland functions. And the second step would be creating a triangulation using a set of simplices and interpolate the values of the optimal recovery at these vertices by a continuous piecewise affine function. We call it CPA function. Now, the thing we want to do is that to check the conditions for this CPA function if it satisfies the constraints of contraction metric. So the verification problem consists of two constraints to check whether P is positive definite at each vertex or not, and the negative definiteness of the operator A nu plus some error terms. A nu, as you can see here, is more or less the same as the F we had before, and the extra term here is to guarantee that if these conditions hold at every vertex, then any other point inside the simplex, the conditions we want is also satisfied and verifiable. Now, the constants you see here are the second order derivatives of components of F and third order derivatives, the diameter of each simplex, the dimension of the system, and upper bounds on P and the derivative Pij. A little bit about the complexity of the algorithm. For the first step using RBF, the complexity is of order n RBF power 3 and 6, where small n is the dimension of the system and n RBF is the number of collocation points. For the second step verification, we need to verify everything at each vertex for the first constraint, which the complexity would be NCPA and RBF. And for the second constraint, we need to do it at every vertex of each simplex. So if they have common vertices, we need to do it twice and more. Now it's good to remember that the number of simplexes in the triangulation is bounded above by NCPA and factorial, and it shows how the complexity grows as the dimension of the system grows. Now, if the constraints of the verification are satisfied, then we can say that, well, we would have a contraction metric in the area, which means we have P positive definite at every X, not only the simplest vertices, and FP being negative definite at, again, every point, not only the vertices. Also, if we start from a contraction metric itself, we make the optimal recovery, we use the values at each vertices, and then make the CPA interpolation, doing all the settings accordingly, we can guarantee that, well, these functions made in that way satisfies the constraints of the verification problem. So in fact, this CPA interpolation itself is a contraction metric. Now, the property I would want to show you in a few seconds after this is the robustness of the contraction metric. It doesn't really depend on the exact location of the equilibrium point. So if we have a perturbation of the system, we would still have the same contraction metric working for the new system as well. The example I have considered the following, a 3D example I decided to have, and we could find the Bayesian of attraction for the origin, the stable asymptotically stable equilibrium point of the system analytically, fortunately. We use the Wendland functions and with parameters C 0.9 and the following size 0.4 for it. And the number of collocation points is 1,331, which you see comparing to the number of vertices we need for the verification is very little. Now, for the whole area, you are seeing the positive definiteness is satisfied, so you don't see any problem here about that. The black dots you see are the set of collocation points, and the green surface you are looking is the boundary for the area where the second condition, negative definiteness, is not satisfied. So inside this area, we would have both conditions, positive definiteness of P and negative definiteness of FP satisfied. Now, in order to have a comparison with another method, we make a Lyapunov-like function, and we try to find a level set of the system by trying to approximate the Bayesian of attraction. Now you see that we show the failing points of the Lyapunov-like function by the blue dots, which is where the orbital derivative is not negative, and the red set is a level set of W. So you can see inside the appropriate area adjusted by the contraction metric method, we have a subset of the Bayesian of attraction and everything is okay. Now, the interesting point is that if I consider a small perturbation in the system, And I added these two terms here and this multiplicative term in the third dimension, and consider two values for the epsilon, a small one and a bigger one. And then what we're going to do is that we use the same contraction metric and Lyapunov-like function calculated for the original system, and now do the verification for the perturbed system. So we change the right-hand side with the f of the perturbed system and see how things go. For the small perturbation, you see still the contraction metric is good. The green surface is a little changed, modified. You can see it up here and down here, and also a little visible in this area, but it's still quite very good and almost the same as before. And the Lyapunov-like function also works well. The failing points increase a little, but not stops us from using the same Lyapunov-like function. And the level set change, but it still is good and inside a suitable area. Now, for the bigger value for epsilon, you see the contraction metric evaluation changes a lot. It's still good in a great area, but you see the big difference is very much visible here. The problem here is that the Lyapunov-like function fails to work. As you see, the blue dots are always not only around the area, but also inside and on the boundary of this red set, which is not desirable. So what we had to do was we had to compute a new Lyapunov-like function, which now you see the failing points are outside the desired area, and we have the red level set inside the area suggested by the contraction metric, and everything works fine. So you see that while for the small perturbation, both methods seem not so sensitive with respect to perturbations, but for smaller ones, for bigger ones, the contraction metric was still robust with respect to perturbation, while the other one failed. Now, I entered in the abstract of the talk, I also said I would talk about the periodic orbits, and it will be very short. The thing we need to change are very little, but the whole idea and the algorithm is more or less the same. So I just give you an insight about it. If you remember here in the big term, we had df here only for the equilibrium point case. Now for the periodic orbit case, we need to change it with v, which is defined in the way suggested by equation 10. And well, it comes from the idea of doing it in a specific direction. But changing this and small other things along the way, we would be still able to use the same, more or less the same algorithm and the same method to compute the contraction metric for periodic orbits. I omitted the example for this because I didn't think we would have enough time, but well, I ran very fast and think that well, it was okay. Thank you for your attention.
Thank you, Iman, for the nice talk. But I don't know if someone has any question or comment. I have some questions. The first, maybe you explained it that along the top, but I was kind of lost. Why you need to go the third derivative?
Yes. For the verification problem, maybe here, I need some upper bound when I'm doing the verification at each vertex. If I approximate something more, then we prove that we can guarantee that it holds for every point inside the simplex. In order to get that upper bound, we need these second order and third order derivatives of f.
Okay. And
That goes with the theorem.
can you go to the slide number 13, before of that?
Yes.
So you create a triangulation, now it's clear to me. No, nothing. My question was why simplices instead of another polyton, but it's because of the triangulation that you need.
Yeah. So we can have this linear form there later. Yeah.
If someone has any question or comment. And for the verification, you use C++ also, or?
Yeah.
Oh.
Yes. Yeah. At the beginning, we use MATLAB, and we have some papers on the comparison of MATLAB and C++. But at the end, when you need to care about the memory and you need to use all the memory of your system, it's better to go to C++, so you can design everything you want.
Okay, let's thank the speaker. If no one has questions, and we move to
maybe it's better we move sooner to the next room and get ready for the second part of our talks.
Thank you, Iman, for the nice talk.
Thank you.
Hello, Doug. I said before, I have the kids at home, so I will stream my talk. Can you hear me? Can you hear me?
Yeah.
Okay.
Yes.
Okay, so we'll wait 2 minutes, or?
We can start if you will.
I can start, yeah. Okay, so I start the talk and then I mute myself, I hope. Welcome to this talk on Lyapunov functions for nonlinear systems by linear optimization. Lyapunov functions are something like a dissipative energy for dynamical systems. And if a Lyapunov function for a dynamical system is known, then we know a lot about the qualitative behavior of the system. And well, here in more detail, we consider an ordinary differential equation here, x dot equal to f of x, where f is a vector field from Rn to Rn. And we assume that it has an asymptotically stable equilibrium at the origin. And we let B be its Bayesian of attraction. So if the solution, if the system starts at point C at time 0, then phi of t comma c is going to convert to 0 as time moves to infinity. And here this phi t of c is the solution starting at c at time 0. And its position at time t is then given by phi of t comma c. And equivalent to a system with that it has an asymptotically stable equilibrium at the origin, with Bayesian of attraction is that there exists a smooth function v from the state space to the real numbers. This function has a minimum at the equilibrium point at the origin, and the so-called orbital derivative of v, this is here given by the gradient of v at x dot product with f of x, is less than 0 at all points in the basin of attraction, except for the equilibrium point at the origin. And well, the basin of attraction is then can be characterized as a sub-level set here of this Lyapunov function, this smooth V. And well, this orbital derivative, this is just a very convenient way to see that V is actually decreasing along all solution trajectories of the system. So if you see here, you take the time derivative of V of phi at tc, at time t equal to 0. Then with the chain rule, we get this formula here. And so the trick of the Lyapunov function somehow is that, well, we just check this condition here at every point C in a domain. And well, if it is less than 0 in the whole domain, then this function must be decreasing along all solution trajectories passing through the domain. So we have here kind of eliminated the solution, or the formula for the solution, because of course we usually don't know the formula for the solution, and it's, well, in general, it's impossible to get a formula. You can at most do some, have some numerical schemes to generate solution trajectories for some particular initial values. And so this formula here, well, wouldn't be really useful unless that we can somehow eliminate the solution from the conditions here. And these are the conditions for a Lyapunov function. And as said here, if we know that if we have a Lyapunov function for the system, then we also know that we have a stable, asymptotically stable equilibrium point of the system. And we can also get the basin of attraction from the Lyapunov function, or from a good Lyapunov function at least. The CPA method, where CPA stands for continuous and piecewise affine, is a numerical algorithm to compute a Lyapunov function on a compact domain for a system with a stable equilibrium, or an asymptotically stable equilibrium. And I want to describe the method in, well, quite a detail. So we'll just concentrate on the simplest example, where, well, the simplest non-trivial example here in the plane, so R2. And but it works exactly the same in n dimensions. I've also mentioned that always when I'm describing it in 2 dimensions. And well, equilibrium at the margin simply means that f at 0 is equal to 0. So if we are at the origin, then nothing will change, because then x dot is equal to 0. There's no movement. And D is then a compact neighborhood of the origin. And the Lyapunov function we want to compute is then a function V from this compact domain, this compact neighborhood of the origin, that is continuous. It is 0 at 0. And well, let's just say here that V at x is larger than or equal to the Euclidean norm at x for all x in D. So this implies then that it's a minimum at the origin, and this is not restrictive. And then we demand that the so-called Dini derivative, well, from the right of f is less than or equal to minus the norm of x. The reason is that we cannot really use the derivative, because our function that we construct is well, it's continuous and piecewise affine, so it is not differentiable. But this here, that this is negative, will also imply that V is decreasing along all solution trajectories. So this is enough. And like I said, well, it works exactly the same in for f defined from Rn to Rn. And here we assume that f is 2 times continuously differentiable. It is not quite necessary, but it's convenient. And the method works as follows. We take the domain where we want to compute our function, and we cut it into triangles in 2 dimensions. And in n dimensions, we will cut it into simplices. The most convenient way of doing this is just to cut here Rn, or here R2, the plane, into very regular triangles, and then to map the triangles into the domain. And we map the triangles by mapping the vertices and redraw the triangles here into dimensions. So for example, this function here, large F, capital F of X, here is some scaling function, and this here means that we map boxes into circles. It is usually more adapted to the symmetry of the differential equation. And after this, actually, we can map it very conveniently from this form to, well, at least all ellipses, ellipsoids, and such forms. And here, well, for this figure here, we use this particular form here. So this rho is just a scaling factor, so it's constant, and times the infinity norm of X. And then we have this factor here, infinity norm of X divided by the Euclidean norm of X and times X. This triangulation has to be shape regular, as it is called in finite element method. In many other places, it's called a simplicial complex. So it basically means that two simplices, they intersect in a common phase if they intersect at all. Yeah, the idea is to construct a linear optimization problem such that a feasible solution to this linear optimization problem delivers a Lyapunov function for the system. And here we take for every vertex of the triangulation, so here is the whole picture, and here it's zoomed in, here is a particular simplex as nu. This particular simplex has three vertices, x0, x1, x2. So we make the variables for our linear programming problem v at x0, v at x1, and v at x2. These will be the values of the Lyapunov function also at these points. And then we have some auxiliary variables here, c nu1 and c nu2. And these will be used to get a bound on the one norm on the gradient of the Lyapunov function on this simplex here. And note that, of course, that v at x0, well, this vertex is shared by many other triangles. So it's not enough here just to look at this one. We also have conditions for these variables for the other triangles where it's a vertex. And, well, how do we make the constraints? So the main idea that will be used throughout is that every point in this triangle here as nu, which is the convex combination of the vertices x0, x1, and x2, can be written uniquely as a convex combination of the vertices. Here x is equal to the sum from I from 0 to 2, lambda I and x, xi. And these are positive numbers that sum up to 1. And what we want to do is we want to define our function v at x as the same convex combination of the values of the variables at x0, x1, and x2. So v at x will be the same convex combination as here above, but now of the values vxi. And to enforce v to have a minimum at the origin, this is the very easy part, we just put v at 0. So when the vertex is 0, put it equal to 0, and v at any other vertex x should be larger than or equal to the norm of x. And we do this for all vertices of all triangles. And of course, then we also need the origin to be a vertex of a triangle. And well, if we do this, then v, which will be our interpolated function here, at 0 will of course be 0. And for any x, we can simply use that the norm is a convex function. So we have this inequality here. So v of x will always be larger than or equal to the norm of x, the Euclidean norm at x. So this is the easy part. Now we come to the more difficult part, and that is to ensure that the function we construct really has a negative orbital derivative everywhere except at the origin. And well, we cannot really check this for all x in the domain D. So the whole trick of this CPA method is essentially to demand at the vertices of all triangles a little bit more. So you see here minus norm of xi is larger than or equal to here the gradient of v at mu, and this will be a constant vector on a very simplex. We give the formula on the next slide. And then dot product with f at a vertex xi of the triangle as nu. And then we have here plus e mu I times the one norm of the gradient. And this quantity here will be chosen such that if this is fulfilled at all the vertices, then we really have that the minus x, minus the norm of x is larger than or equal to the gradient of v dot product with x at x for every x in the simplex, in the simplex of the triangle, and then because this holds for all triangle or simplices in the domain, this will hold for all x in the domain. And this quantity here, E nu I, is defined as B nu, which is an upper bound on the second order derivatives of the components of f, and then times something that only depends on the simplex as nu. And this is then implemented in two steps, this linear constraints. So here, the gradient nabla v nu of v in the interior of the simplex is, it's easy to see, well, v of x is given by this convex combination of the values of v at the vertices. And since it is a fine function here, we can write this as some vector here, we could call nabla v nu, dot product with x minus x0, basically just pick one vertex of the triangle, and then plus v at x0. And the formula for this nabla v nu is then given by a matrix times a vector where the components of the vector are vx1 minus vx0, vx2 minus vx0. And you can imagine how this looks at higher dimensions. We just go with more vertices down. And this matrix here is the inverse of this matrix here, x nu, which is gotten simply by writing x1 minus x0 in the first row, x2 minus x0 in the second row, and higher dimensions, so on. And to ensure that, to get a bound on the one norm of the gradient of v nu, we essentially use this here. We use this auxiliary variable c nu j for j from 1 and 2. And well, if this here holds, this constant here, then the one norm of the gradient is definitely less than or equal to the sum of the c nu j's. And well, this matrix x nu and then its inverse only depends on the geometry of the triangle S nu, and in higher dimensions on the geometry of the simplex S nu. And the orbital derivative of v is forced to be decreasing by demanding this, as we said. And here is this quantity E nu I, and B nu is this constant here. It's an upper bound in the second order derivatives of the components of f. And this is actually the only non-trivial inputs to the CPA method. I mean, we use the triangulation and then we construct the linear optimization problem. Everything can be done automatically except that we need to deliver some values here to this upper bounds. But in practice, this is usually very simple because there is an upper bounds. This is not the maximum, it's just something that is not lower than the maximum of this second order derivatives. And well, now comes the trick. Now we assume that these constraints are fulfilled. These constraints here at all vertices of the triangle S nu. And now we have a look at the general x that in the triangle S nu. which is then a convex combination of the vertices. Well, if we now write the gradient of V nu dot product with f at x, we can, well, split it up like this. Well, we are adding this term here and subtracting it here immediately again. And then by Hölder's inequality, we can estimate this dot product here from above by using the one norm of the gradient, which is less than or equal to C mu1 and C mu2, times the infinity norm of f of x minus this convex combination here of f at the vertices. And then we have a theorem that tells us that exactly with these constants here, well, what we call E nu I, it's exactly like this. In our case, we were having n equal to 2, so this cancelled out, that this here will be less than or equal to the same convex combination of these E nu i's we had before. So from this theorem, this here follows. So if we keep on with our computations here, then you see that we can replace this here with this, the convex combination of these guys here. And well, the constraints were that this here is less than or equal to minus the norm of xi, the vertex xi. And now again, we can use that the norm is a convex function, and get that this here truly is less than or equal to minus the norm of x. And here is just a short note on how to select this x0, how to choose. We had like some vertex that had some special role in the triangle we choose. And well, essentially it is that it doesn't really matter, except when the origin is a simplex, is a vertex of the triangle, then we have to choose x0, this main vertex somehow, as 0. The reason is that otherwise we could not fulfill this here. However, if x0 is 0, then it simplifies and we don't actually really have to check anything at that vertex because it will be automatically fulfilled. Okay, so from this it now follows that if we have a feasible solution to our LP problem, then the function we defined as this interpolation is continuous and affine on every triangle of the triangulation. It will be 0 at 0 and will be larger than the norm of x at any point x. And this here will hold. So if you take this dv derivative of v, then it will be less than or equal to the minimum, but we're taking the minimum here over all nu such that x is in the triangle as nu. And well, and this will be less than or equal to minus the norm of x. Taking this minimum here over all nu's is only important when we are at the, so I mean, some points belong to more than one triangle. And since this is checked for every triangle, this will truly hold. And from this, it follows that V will really be a Lyapunov function for the system. And note that it is a true Lyapunov function. It's not an approximation to a Lyapunov function, which wouldn't be very useful. It truly is a Lyapunov function. Okay, just to show how this works in action, well, we take here some two-dimensional system. It's simple to get the upper bounds and the second order derivatives. We will automatically generate our domain and the triangles, and we generate our linear optimization problem. We solve it with some solver. We'll usually use Kuropi because it's a very nice linear optimization solver. We get a feasible solution. The feasible solution is plotted here. So these are always the values we get for V at the vertices. And then we interpolate them as described before. And well, now this is the graph of a Lyapunov function for the system. Here in 3 dimensions, well, here it is a little bit more difficult to see what is happening, but it's exactly the same methodology. No, so what we have seen is that, well, if we get a feasible solution to a linear optimization problem, then we have a Liebner function. This was, well, it was proved, the first version of this was proved in 2002. And it was essentially by adding these terms here, but without these terms, this was done a few years before, mainly by Julian. But then some a posteriori analysis of the function had to be done. And it could never truly be, well, have a negative orbital derivative close to the equilibrium. By adding this term, we can actually construct a Liebner function that goes to the equilibrium point. And like I said before, the unusual part of this numerical method is that it delivers an exact object. So it delivers a true Liebner function, not an approximation. And the reason why this is possible is because this here is an inequality. So it's basically a partial differential inequality, not a differential equation, differential inequality. But, well, it is nice to have a method such that if we get a solution, then we get a Liebner function, but it's of course much, much nicer to have something that somehow always works. So that we want to prove that this always works in the sense that if there is a Liebner function for the system, then this method can compute one. And this is true for this method, and it makes it particularly nice. And, well, I will first describe it in a little simplified setting where we exclude some neighborhood close to the equilibrium point. And these were the first results on this problem. And what is proved there essentially that if you make the if you make the linear programming problem, and the simplices are small, and they also have to be in some sense regularly shaped. That means that this quantity here should be bounded even when we make the simplices smaller. And, well, it's not difficult to do this. It's not difficult to make a sequence of triangulations fulfilling this. And the idea of the proof is that, well, if we know there exists a Liebner function, or equivalently, if we know that the equilibrium point is asymptotically stable, and we take some subset of the basin of attraction, and we pick out or cut out a small neighborhood n of the equilibrium point, then we can use the function, the Liebner function W, which we may assume is C infinity, to assign values to the Vx at all the vertices of the triangulation of a linear optimization problem. And here we know this Liebner function W here exists. We can also assume that it's larger than or equal to the norm at every point x in here. And we can also assume that the orbital derivative of W is less than or equal to minus 2 times the norm of x. And here we just sign at all vertices of the triangulation V of x equal to W of x. And from this we can construct the C nu j's. And, well, then this here will be trivially fulfilled simply by construction. And this here will also be fulfilled because we can estimate the difference between the gradient of V in the nu, in the simplest S nu, minus the gradient of W at x0, where x0 is just one of the vertices of the triangle. It will be bounded by some constant A times here then the one norm of the this matrix X, inverse of this matrix X nu we talked about before. And this, well, only depends on the geometry of the simplex times the diameter of the simplex, or in two dimensions triangle, squared. This bound here, we can get a bound here for the whole domain because it's compact. And since we assume that we are using triangulation so that this here is bounded, and this here is going to 0, then this estimate here will go to 0. And yeah, so this can be proved used to prove that this will always be fulfilled for small enough triangles. If you want to do this in the full setting, and this was a result that we did much later, we don't really have to cut out this small neighborhood close to the origin. It's much more difficult to prove, but it can be done by using a certain Lyapunov function here close to the origin. So basically it uses a linearization at the origin, computes a Lyapunov function for the linearization. And then these two Lyapunov functions, this local one and the global one we had before, can be agglutinated in a certain way, so that the result is still a Lyapunov function. And well, there are some challenges to prove. I'm not going to go into details because it gets pretty complicated, but one can still prove that the linear optimization problem has a solution. Here one needs triangulations. Well, there is simply not enough structure in a triangulation like this here close to the origin. So one needs so-called what we call triangle fan at the origin. And yeah, so it's plotted here in 2 and 3 dimensions. So we need more triangles close to the origin. Okay, so now I'm just going to sum up a little bit about the CPA method, and then I'm going to show you a lot of pictures. So what we showed here, well, in a very short manner, is that it is essentially constructive. So if there exists a Lyapunov function for the system, then we can always compute one. And well, if there doesn't exist a Lyapunov function, then we might make our simplices smaller and smaller and smaller, and we never get a solution. So it's like semi-decidable. However, this is not really a problem because local stability is not the problem. The problem is to get a good estimate on the basin of attraction. And for this, it's easy and good to use this method because we can just check local stability in a rather quick way, and then we try to compute a CPA Lyapunov function on larger and larger domains and to get good estimates on the basin of attraction. And yeah, I will just leave it at that. This is okay. And if we now try to sum up what are the good things about this method, well, the good things are we construct a true Lyapunov function for the system. There is no posteriori analysis of what we compute needed. It works in n-dimensional from general non-dimensional systems. So actually, we only need it to be C2 or yeah, more or less C2. Actually, we can live with a little less than that. It's constructive in that it always works. If there is a Lyapunov function, we can use this method to compute a Lyapunov function. And it's very flexible. And this is just the general idea for the simplest kind of system, but also, actually this idea generalizes to many other kinds of systems and actually also to contraction metrics, which we have been talking about today. Well, what is not so great about it is the speed. Well, we get a linear optimization problem with a lot of variables. And well, there are much faster methods to compute something. I mean, solving a system of linear equations is, well, the number of variables cubed, here it is to the power 4. So yeah, this could be better. And others are that, well, programming this method, almost all the energy goes into the triangulation. And local refinements of the triangulation, because it's hyperregulars, are not so easy. The Lyapunov function we get, it's not a smooth function, it is piecewise affine. And there is no formula for the computed Lyapunov function. Some might consider this as a disadvantage. And like I said, the general idea can be extended to many other kinds of systems, like to differential equations or switch systems, which are almost the same thing. It can also be extended to contraction metrics, both for systems with exponentially stable equilibria or periodic orbits. And what is a very nice feature is that you can combine it with faster methods. So we use a faster method that does not give us as much guarantee of the computed object as the CPA method, but methods that compute, well, they compute an approximation to a Lyapunov function. This approximation will also be a Lyapunov function if you are using a grid that is dense enough or something else. But we never really know when this object we construct is truly a Lyapunov function, but then we just use the CPA method to verify the object we constructed with a faster method. So then the idea is we compute something that we think is or might be a Lyapunov function. So we compute a Lyapunov function candidate. Then we make a triangulation and we assign the values of the object we computed, the Lyapunov function candidate, to the variables of our linear optimization problem. And then we can verify if the CPA interpolation of these values is a Lyapunov function. And then if they are fulfilled, this is a true Lyapunov function. And well, another nice part about this procedure is that, well, if it fails, we actually see where it fails. If we are solving the linear optimization problem, it only tells us, well, we have here an optimal solution, or it tells us there is no solution. But it doesn't really tell us why there is no optimal solution. It doesn't tell us where the problems are. Okay, and now I'm just going to show you this RBF approximation. This is a collocation method to compute Lyapunov function. I'm not going to talk about it here because Peter talked about it earlier today. Here we use a 7x7 grid to compute, which is much too little for the system here, but this is to show you how it works in practice by using more collocation points and finer triangulation in every step. You compute here an approximation to a Lyapunov function. Here is the triangulation of the same area. We assign the values here of this Lyapunov function candidate to the problems. Then we verify the constraints. You see we make an X everywhere where they are not fulfilled. So they fail in a lot of areas. But then we use a much finer grid here, 19 times 19, for the RBF method. We get this function here. And we use a CPA interpolation with more triangles. And now you see it succeeds everywhere except very close to the origin. And actually we cannot guarantee that this works close to the origin, but we can guarantee that this works everywhere except very close to the origin, an arbitrary small neighborhood. Here, another system, again, very loose grid, few collocation points for the RBF method and large triangles for the CPA method, so it fails here in a lot of triangles. Then we use more collocation points and smaller triangles, and it fails a little, much less, only here closer to the origin. And then we take even more triangles and more collocation points, and it fails even less. And here, well, it's the same function from the RBF, so it's the same object we computed, but we use a finer triangulation for the interpolation, and now you see it's failing only very close to the origin. And we could go so on. You see, here it is failing in 6 out of 648 triangles. Here it is failing in 4, and only 4 here, closest to the origin of 2,592. Okay, we don't need to use the RBF method. It's just a nice method to compute Lyapunov function. We can also use other methods to guess the values at the vertices. Here we are computing the length of the trajectories of the system, from where time runs from 0 to capital T. And this is here a system with 2 equilibrium points, and actually, so these here 2 are equilibrium points. Both are stable. And from the level sets of the Lyapunov function, we computed and then verified. We get here, well, level set, everything starting here will go down here, everything starting here will go down here. And we actually see this boundary between these basins of attraction quite nicely. Here for another system, this is a system from biology, also with 2 equilibrium points, and you see this also here, and you see the separatics quite well. And well, everything starting in our sublevel set here will go to this equilibrium point, everything here will go to this equilibrium here. We don't necessarily need to take the length of the trajectory if we know where the equilibrium, it's just nice because we don't really have to know where the equilibrium points are. If you know that where it is, and here we can then always assume that it is at 0, here like for a 3-dimensional system, we can use other formulas. Well, for the Lyapunov function, one can show that these formulas always involve the solution trajectories, which we don't know, but we can approximate them starting from some initial values. And the initial values will then be the vertices of our triangulation. And here, well, we use 2 different formulas. This one comes from Yoshizawa, and this one, well, we can say from Kurzweil. And here we get nice Lyapunov functions for the three-dimensional system. It's failing here in the blue dots. This is actually separatics. And well, we cannot really plot the Lyapunov function in compute, but we can compute, we can plot level sets. So you see here, everything starting in the red ball here will go to the equilibrium at 0. Everything starting in this red set here will go to the equilibrium at 0. And just it's quite dramatic how much faster this is. So you can take the same system and actually solve the linear optimization problem. It will, well, in a particular computer, it took 1 hour, and this was the largest level set we got from that. So everything starting in here would go to the equilibrium at 0. This took 1 hour in comparison to 10 seconds for the computation of each one of those. So, and the results are better. So then I just thank you for listening, and please ask questions if you have any. Hello, I'm here.
Thank you, Siggy, for the clear and nice talk. I don't know if someone has any question. Yes. Margarita Camarinia say, thank you for such interesting talk. What about applications of these methods to celestial mechanics?
Well, we would be very interested in doing that, but we have not done it. So if you have nice systems you would like us to analyze, then we would be happy to do.
David Martin de Diego say, thanks for your nice talk. In control theory, a method for stabilizing under actuated mechanical control system in fluctuating systems is by imposing kinematic constraints, call it Lyapunov constraints. That is, we find a control function based on a constructed Lyapunov function. I think that perhaps it would be quite interesting to use or to adapt your construction techniques for this type of problems. For instance, to stabilize a controlled pendulum on an unstable equilibrium of the uncontrolled pendulum, etc. I don't know if you can access to the question, to read the questions, or...
Oh, wait a minute. Is it in the chat?
Yes. There are 2 chats. One of them is for questions.
Q&A. Yeah. Okay, yeah, we would have to discuss this, I think, when we have more time. So it is actually possible to do different optimization problems where you try to compute a control Lyapunov function at the same time. However, there you would need something like mixed integer programming, which is, well, much slower, and I'm not so sure how to implement it without having some knowledge of the system, you know, so you need some knowledge to simplify it quite a lot, like to have rather large control regions, because, well, if you have 2 possibilities of the value of the system in like one area, that will lead to an integer variable. So if you would like take every triangle or every simplex in such an optimization problems, you will simply have too many. You would, well, theoretically you should get a solution, but in practice you would never get it. But yeah, I would be very interested to discuss these things. I mean, we are really searching for applications for our methods. We have been developing methods for many years. Peter here for many years, and also Iman and Carlos, and we would be very interested in applications. So please contact us if you have some ideas.
Thank you, Siggy. I don't know if someone else has any other question or comment. I'm going around the same question as with Ayman. Can you explain me, please, why you need a triangulation with triangles instead of cover the space with other simplices, with other polytopes? Sorry.
You would like to use other polytopes than and simplices in interventions.
Sorry, say again?
Is the question if you can use other kind of polytopes in this?
Yeah, that's my question, yes.
Well, then you will run into problems because you want the gradient of the Leibniz function to be constant on the areas, and you want the function you get to be continuous. So if you want it to be piecewise linear, which this method is based on, then I really think you need n simplices. But I mean, if you have other polytopes, you can just cut them into simplices, so it's not really limiting.
Yeah. Thank you. David Martin de Diego say about the other question. We can discuss about this, of course. Sigi, thanks a lot.
Thank you.
If there are no more questions, then we can close this first session, and then we need to switch to another stage. Okay? So I think that, let me corroborate the name of the next stage. It's called Salvar Nunes, and we start in around 20 minutes. Okay, thank you very much to all the speakers. I don't know if Ayman wants to say something.
No, thank you a lot, and see you soon in a few minutes.
Okay, see you.
Yep. Thank you.
Thank you. Bye.